Okay, really sorry for that, guys. I think for all the lectures, I think for this one it won't be too big of a deal. We're mostly going to work through some examples and even maybe 20% of the slides are ones you've actually seen before, so we're kind of going back over a couple concepts related in part to gradient waveform design for slice selection, phase encoding, and the readout gradient. So sorry for the goof. The slides will still be available online. In fact, the right slides. So anyway, we'll get rolling with that. So this is just a reminder. We have lab next week, and these are the groups. I didn't hear any sort of problems or conflicts or anything, so I'm assuming we'll just go with this. And this lab is more likely to run a little bit more on time. We've done this lab several times, aside from the sort of just whether or not we can start exactly at 6 or not. But you'll mostly just come right in and start the lab right away. There's no kind of pre-lab demo. We're not going to, unless you have ideas, we're not going to be playing with the magnets, so to speak. So anyway, these were our learning objectives from the previous lecture, right? So we talked about 2 different kinds of chemical shift artifacts, sort of what their origin is, and maybe how we go about mitigating those. So who wants to remind me of what type 1 chemical shift was?
Spatial misregistration.
Thank you, right? So fat can appear in an image that is sort of spatially dislocated from where it actually occurs. And then there was type 2 chemical shift, which was related, it had another name that's sometimes helpful. It was called an India ink artifact, right? And what kind of feature did it present in an image? The India ink artifact is sort of a good giveaway name, right? Looked like ink. Right? Well, let's think a little bit about what did type 2 chemical shift artifacts come from? Why did they arise? Between so fat and water have different resonance frequencies, and so at particular times they might be in phase or out of phase. If fat and water are in phase with one another, they constructively will add together, so you'll just have kind of a relatively normal appearing signal amplitude. But what happens if they're totally out of phase with one another? They can basically cancel each other, right? And so the signal, assuming their magnitudes are similar, right? So if their magnitudes are similar and their directions are completely opposite, then they can cancel out each other. So you get these dark kind of streaking artifacts, in particular where fatty tissues are adjacent to watery tissues, because there will certainly be pixels that partly contain fat, partly contain water. And so if you want to, say, mitigate a type 1 chemical shift artifact, that means kind of make it not quite as bad, what are your choices? So type 1 was the spatial misregistration. Right? So for spatial misregistration, we could adjust. It was an acquisition parameter. Bandwidth. Thank you. Right. So we can go to a high bandwidth acquisition. We'll have less shift because the frequency per pixel is higher, but the frequency shift for fat is constant for a field. What's the downside of increasing our bandwidth? SNR. Right. So high bandwidth acquisitions will tend to have noisier images. So there's noise trade-offs. For type 2 chemical shift, we sort of said it already. We can have fat and water be, say, in phase or opposed phase. And what is it that controls how in phase or out of phase they are? TE, right? So the time after excitation to when you're actually forming your image. They could have various amounts of phase relationship to one another, either being completely in phase or opposed to phase. We have 2 different partial Fourier acquisition methods, right? So we could do partial Fourier in what 2 directions? KY and KX, right? KL and KP. Yeah, so 2 different directions, right? So the frequency encoding direction and the phase encoding direction. What was the advantage of having partial Fourier in the readout direction? What does that do to your sequence? A little bit faster, but not too much faster. Decreased TE, right? So mostly, this is our sort of K space, right? So KX and KY. And if I don't have to read out as far this way, then by the time I read across this way from my line, the time it takes me to go from here to here is shorter. And so for partial Fourier method, my echo time can be reduced. And why is short echo time good? Or shorter echo time good? helps your signal to noise, right? What's the downside to partial foyer? There's at least two. Motion artifact in the readout direction shouldn't matter too much. Anytime we scan faster, what happens to our signal to noise? It goes down, right? So partial foyer methods, regardless of which one, you're going to have reduced signal to noise, but you're going to increase your decrease your echo time, so you'll buy back some signal to noise. What was an artifact associated with the partial foyer methods?
In the middle, zero filling.
Yeah, and so zero filling leads to different possibilities. Do you remember? You could get some kind of you'll get some kind of almost like an aliasing or ghosting artifact, but you'll also get some blurring. It'll broaden your point spread function. The other possibility, so that was one Fourier acquisition method in the readout direction. You can also do partial Fourier in the phase encode direction. What does that mean in terms of the number of KY lines you require? Goes up or goes down? Goes down. It's partial Fourier, right? So what's the advantage to partial Fourier in the phase encode direction? Reduce TR. Won't change our TR because we're still have same echo time and same time to repeat getting a line. Say it again. Someone said it. Just faster, right? Fewer phase encode lines, you're going to scan faster. But every time we scan faster, our SNR goes down, right? So there's always trade-offs. So then we talked about some possible strategies for scanning even faster, right? And these are kind of big deal approaches. I mean, if you go back to the 80s and read papers, people were imaging for 20 minutes and 25 minutes and things like this, right? So lots of tips and tricks. You'll learn about some more in next week's lectures as well. But one strategy was called multi-slice imaging. Why was it that we could do multi-slice imaging? So if you think of the spin echo sequence, what was kind of wrong with the spin echo sequence? Yeah, long TR, and then you have a long TR, that means what? Wasted time, right? There's a bunch of time in that sequence where maybe you're not doing anything. And so the advantage of this approach was significantly decreasing your acquisition times, right? There's some different disadvantages, mostly related to possibly SAR, right? You're going to play a lot more, say, RF pulses per unit time, so the SAR could go up for those strategies. And it doesn't change. It still takes just as long to get one slice of data. It still takes the full 5 minutes. You're just able to get many slices in addition within that same sort of 5 minutes. So then we also talked about multi-echo imaging as another strategy, right? So not just exciting once to get one echo, but exciting once and getting a second, third, fourth, 16th echo, right? So what's the advantage of multi-echo acquisitions? What happens to scan time? Up or down? Down, right? So it's a lot faster, right? What happens to your signal to noise? It's going to go down, right? It's not going to be quite as good. Those second, third, and 16th echoes are much lower in amplitude, for example. So you have lower signal to noise. What happens to your point spread function? Does it ever get narrower? Unfortunately not, right? If you solve that problem, you'll get a prize, right? But usually, think imperfections, so to speak, are only going to broaden our point spread function. And then at the very end there, we worked through something very practical, which is given a starting protocol, how could you make this protocol overall, substantially faster and make it actually something that a patient, starting from a protocol where a patient couldn't even use it, or you couldn't use it clinically, to getting into a protocol that was perhaps much better. And I think that's kind of a good sort of mental exercise to run yourself through, just as a way of, at least in part, getting ready for the lab that comes on Tuesday, and then just thinking of all the very practical choices that we have to make dealing with different protocols. Okay, so questions about where we were end of last lecture? Okay. So of course I put together learning objectives for this one. We'll come back to these. I'll figure out how to do that because we have a guest lecture next, but you can always revisit them on your own. Works, right? Okay, so some of these slides we saw already, but I want to do it as a reminder for gradient safety, right? So there were several things. What we're going to be talking about today is in part sort of gradient design. And I just want to remind you that, of course, the gradients are the thing that generate all of the noise, right? So MR scanners are quite noisy, and we'll typically need earplugs or headphones for two-way communication. Headphones can dampen the exterior noise and then let you talk with someone outside. And then another consideration is so-called peripheral nerve stimulation. Of course, FDA is concerned about both of these things, right? They don't want the scanners to be so noisy that there's hearing-related problems, and they don't want a scanner that operates with significant peripheral nerve stimulation, because you'll end up with these very uncomfortable sort of tingling sensations or even sort of buzzing sensations, and even if it's bad enough, kind of almost like sharp pains, typically towards the edges of the scanner itself. So we'll talk about why that happens in just a second. So this, I think, actually there's some audio for it, but the bottom line is the scanners can be really noisy. The main reason is, and you'll see some of this when we look at the gradient timing today, but the gradients, they're switched on and off on sort of a millisecond time scale, right, or even sub-millisecond time scale. And that will induce some kind of vibration on a millisecond or sub-millisecond time scale. And if you're vibrating the hardware, imagine you're tossing giant currents through this gradient, and it's going to deform even slightly and create audible noise in the 1 over milliseconds range, right, which is the audible range. And so it generates acoustic noise, and it's a really challenging engineering problem that has not, I think, to anyone's satisfaction, actually been solved. They're quieter than they used to be, but still not quiet, even though the manufacturers will advertise their whisper gradients. So, I mean, this is just sort of to set the standard of how noisy is noisy. Obviously, there are things that are much louder. MR gradients under so-called full load will be quite loud, but under sort of standard loads will be a little less noisy, but all the same, these are noisy things, right? So if you've been in near or around the MR scanner, you already know how loud it can be. The other thing we have to worry about is the gradient maximum, or at least we should give it some consideration. But the Gmax, right, so we can turn these gradients on. They typically can be everything from off to on at certain amplitudes. And depending on the specifications of your hardware, they'll have a certain gradient maximum that's possible. But they don't really contribute that much B0, right? The B0, they contribute they don't contribute that much B field relative to the already existing B0 field, which is 1.5 Tesla or 3 Tesla. So the magnetic fields that are exerted by these gradients, the conventional gradients at 4 Gauss per centimeters, you can have really high-end systems at 8 or 30 Gauss per centimeter. But the total field generated by the system, you can just multiply by something like the length of the gradient system, right? That's the linear range over which the gradient system is active. So if it's 30 Gauss per centimeter and it might be a 50 centimeter gradient length to it, then you might have 1500 Gauss, but that's not really that much compared to the 30,000 Gauss that's the 3T field. So the actual magnitude of the gradient fields isn't specifically a concern. What really matters more than the delta V contributed by the gradient is the time rate of change of the gradients, and specifically of the magnetic field itself. So what we worry about is the change in field per unit time, something like Tesla per second or Gauss per second, and there are limitations in place for that. So when it comes to sort of designing the hardware gradients themselves, we typically specify two things: the gradient maximum that's achievable for the system, and then we also specify what's called the gradient slew rate, and that's just the rate of change in the gradient amplitude. How quickly can your gradients get up in increasing amplitudes? But the gradient slew rates that we're allowed to use are actually limited, again, by dB dt, so field per unit time, right? So what matters is how quickly is the field changing per unit time anywhere in your body, and if it changes too quickly, you can depolarize nerves. So it's not really the gradients themselves that matter, it's the field change per unit time. And again, the concern is the peripheral nerve stimulation, and so there's different sort of models, and the details here don't matter a whole lot, but the bottom line is that if the dB dt is on the order of, say, 16 Tesla per second, there's different betas that go into here, but if you exceed these kinds of limitations, then that's when you're likely to experience peripheral nerve stimulation. And there's a bunch of sort of like electromagnetic simulation work as well as experimental work. You can imagine putting 1,000 people through the scanner and measuring who feels something and who doesn't, right? Like at some point you have to do that, right? To build these models, to know that in so-called normal mode, I don't know what the statistics are, but 95 or 97% sort of full gradient power. Whereas you sometimes may need to go to so-called first level mode. It allows for using higher fields switch rates. But when you go to first level mode, there's more likelihood that your nerves would be depolarized. And I don't know what the percentage is, but at first level mode, 90% of patients don't feel anything, but there's still that 1 out of 10 that's going to notice or feel it. And yet, it can only be done sort of in a statistical sense. There's no absolute cutoffs that could be used, except for ones that are really low and would be conservative and would really limit sort of the hardware performance and the system performance. Okay, so we've seen this diagram several times during the class, and we're going to dig into it a little bit more today. This is just a basic gradient echo sequence, and you're hopefully quite familiar at this point with slice selection, phase encoding, and the readout gradients. And what we'll talk about today is how to actually calculate the durations and amplitudes of the different gradients that we need for going through, in this example, the gradient echo sequence. So I'll start with a slice selection gradient. This we know about already, right? The factors that control the overall slice selection are related to the pulse envelope function, and we saw through the small tip angle approximation that it's really the Fourier transform of the pulse envelope function that tells us something about the slice profile. And so we can design this intelligently to give us the slice profile that we want. We obviously have to choose the right carrier frequency so that's matched to the slice of interest. And then depending on the gradient direction and gradient amplitude that we turn on, that will dictate the slice that we actually are able to excite and even the thickness of the slice that we excite. So this is one example that we saw before. We can talk about the excitation bandwidth. So the range of frequencies contained in a slice, right? So we think of slices as having some thickness here, say delta Z, and that might be 10 millimeters or something like that, a typical slice thickness for MR. And then we have the applied gradient that we can turn on, and that will create a range of frequencies across that slice thickness that's equal to delta omega. And so we know that if we pick our omega RF to align with whatever the Z position is, and if we pick our omega RF to align with this Z position here, just through the Larmor relationship, and choose an RF pulse that has an appropriate bandwidth, delta omega RF, then we'll excite exactly this slice, which in this case is it will be, obviously a very, very thick slice. And so then we talked about how we could move the slice along plus minus Z, and one way to do that was just by changing the center frequency of the RF pulse, right? We can move the slice along just by changing the frequency of the pulse so it accords with the slice that we're interested in. I don't have slice B. Here we go. Slice B is here. And so one of the main differences here was just increasing the gradient strength, right? So if we have a higher gradient strength, but we otherwise use the same RF pulse has the same delta omega RF, then we'll be able to excite a thinner slice. And so there's a limit to the thinness of the slices that we can excite, right? What's going to limit that, at least in this example here? What's the thinnest slice you could get?
You don't have signal.
What's that?
It's like it's too thin, you don't have enough signal.
That's true, yeah. So that's it, like in the physical sense, it's a good answer. In the physical sense, if your slice gets to be too thin, then there's just not useful signal, right? And typically in MR, as slices get down to a couple millimeters or a millimeter, you're probably starting to be really starved for signal without a 3D approach. What about your hardware, though? I heard two different answers. Sorry, what did you say?
Ennis.
It's a competition. We should give you all buzzers, right? So the first thing I heard was the gradient strength, right? And so the slope of this line right now represents the gradient strength. How strong are your gradients? And this is, arguably a weak gradient because it only generates a certain field change per unit distance, right? And this is a steeper gradient. If I have steeper gradients, I get a narrower frequency, or I get the same frequency range over a thinner spatial location. The other thing that would control it would not just be not only the gradient strength that you use, the steepness of this here, but it's also the frequency content of the RF pulse. And so there's limits, can be limits there as well. Slew rate is something that it doesn't limit your slice thickness per se, but it could limit your sort of sequence efficiency. That's right. Yeah. But do we do any excitation while we're ramping the gradients? Not usually. It's possible. You can actually design some complicated pulses that we usually think of our RF pulse as looking something like this, and our gradient pulse that goes with this would have a plateau here that we have to ramp up to that plateau. And so and then the slope of this here is the slew rate itself. Right? We don't usually play RF during the ramping interval here. It's possible. You can do that, but it's a little tricky. Okay, so we've described before what we call the time bandwidth product, right, for RF pulse. It's one way of describing sort of the quality of the RF pulse. And it's just the product of the duration of the pulse, tau RF, we use tau as times a lot, and then delta omega RF, so the frequency content, the bandwidth, if you will, of the RF pulse itself. And so we might choose the time bandwidth product. That's a pretty typical thing to do. I can tell you that time bandwidth product of 4 is pretty low, and a time bandwidth product of 16 is pretty high. We don't have a big sort of range of possibilities there, really. And a typical RF pulse might be a millisecond long, and so this tells us that the frequency content, the bandwidth of the RF pulse is about 4 kilohertz. And so we can actually rearrange this expression here to say, well, what's the amplitude of the slice select gradient that I need if that's the range of frequencies that I want to be able to excite, given that I have a particular slice thickness of interest as well. And so if it's a 4,000 hertz bandwidth RF pulse, plugging in some constants here and assuming a 10 millimeter slice, then I end up needing a gradient of about a Gauss per centimeter, 1 Gauss per centimeter. And our systems are typically capable of, 4 to maybe 8 Gauss per centimeter. So you don't oftentimes need full gradient strength to do slice selection. It would be usually below the maximum possible gradient strength. But that's the first step to say, designing the slice select gradient itself. So we could look at this and think a little bit, sorry, I just got a little mixed up there, but we can think a little bit and describe what's the thinnest possible slice that we could excite, right? So we could rearrange just algebraic, really, the expression that we had before. And we can see that as we have, what happens as we have higher and higher gradient strengths? Thinner and thinner slices, right? So we said that before, but here we can see it mathematically. What happens if we have longer and longer RF pulses? We can, in principle, get thinner slices, right? But there's a trade-off right away, right? We don't want typically 20 millisecond RF pulses, right? We typically want kind of short RF pulses. And then we can choose our time bandwidth product as well, but large time bandwidth products typically accord with longer RF pulses also. And so we can get really thin slices with the delta Z that we have is linearly proportional to the time bandwidth product itself. Sorry, the text there. Okay, so how do we actually design, if you will, the slice select gradient waveform itself? Well, you want to ramp up as fast as possible. We don't typically do anything during the ramp process itself, so let's just get up to the gradient strength we need as fast as possible, and then we'll hold it at that plateau for whatever the duration of the RF pulse is. And usually the RF pulse duration is defined for us by the frequency content and the time bandwidth product, for example. And then once you're done with the excitation process, then you just want to ramp down as quickly as possible. And so this would be an example of a pretty typical gradient waveform that we would design or have in mind. And so we can talk about the rate here is just related to the slew rate or the maximum slew rate. And typically we want to operate at the maximum slew rate if we want to be the most time efficient at least. And we know we have to hit a certain target, so that might be the maximum, the gradient amplitude that's used for the slice select. And knowing that slope and knowing that amplitude, that'll dictate the ramp time, or what we sometimes call the rise time. So how many microseconds or hundreds of microseconds it's going to take us to get to the peak gradient amplitude that we need. And then we just hold it on for the duration of the RF pulse, and then we can ramp it back down. And so just picking some typical examples here, we saw a second ago that we needed about a Gauss per centimeter as the gradient amplitude strength, and we're assuming a system here that has a slew rate performance of 20 Gauss per centimeter per millisecond. This is equivalent to 200 Tesla per meter per second, which is another sort of unit that's used for describing the gradient strengths. And so what you see is actually the ramp time is pretty short, right? It's less than a millisecond, so 50 microseconds. And so oftentimes we can ramp to full gradient strength in under a millisecond, or well, almost certainly under a millisecond, under 5 milliseconds, even depending on the specific hardware that you have in your system. And so that defines the ramp time itself, and then you have the plateau time, and then of course you have to ramp back down. So now you have sort of everything you need to know for designing that trapezoidal gradient that's used during the actual slice selection process. But the question is, what do we do about this gradient? And then we have to remind ourselves even what the purpose of this gradient is. So do you guys remember what that gradient's used for? Rephasing, right? And so we saw that when we talked about the small tip angle approximation. But the idea is here we're looking at a set of spins, and we're looking down the axis of these spins during the excitation process, right? And what you see is they end up being dephased at the end of the RF pulse. So they're pointing in every possible direction through the Z direction, through the thickness of the slice. And it's this rephasing gradient here that actually undoes that phase. So there's really no noticeable phase at this point. And once we get to the peak of the RF pulse, now you start seeing this phase dispersion through the thickness of the slice. And all the spins are kind of fanning out as they tip down. And this last gradient here actually undoes all that phase accumulation and can get everything pointed in the same direction. And we want that, right? We want all of our spins in principle pointing in the same, having the same phase relationship with one another, so we get the largest signal we can from that slice. And so it's interesting and notable that the phase accumulation doesn't really start increasing. You'll see it here in just a second. So right now there's very little excitation, there's very little phase accumulation, but as the timing approaches the peak of the RF pulse, things tip over more and begin accumulating a significant amount of phase. And so it's really the second half of that gradient that's really contributing to the phase dispersion in the through slice direction. And so that gives us some insight as to what amplitude we need for this rephasing gradient here. We saw it mathematically through the small tip angle approximation. And there's a term that was the leading term here. Just fix that so you can see it at least. This was the result of working through the small tip angle approximation, and what it told us two things, right? It told us that the state of the transverse magnetization can be obtained through the 1D Fourier transform of omega 1, and omega 1 comes from that B1 envelope function. So there was a kind of one-to-one linear mapping between the envelope function and the slice profile. So that was a convenient way for thinking about how to design the B1 envelope function. But we also ended up with this term in the front, which was the through-plane dephasing, which is present at the end of the slice selection process. So it depended on some omega as a function of z, and that was a consequence of having turned on a GZ gradient. And so we know that omega z, the slice-like gradient that we turn on, generates a frequency according to gamma, the amplitude of the slice-like gradient that's being used, times the spatial position that you're at. So you'll get a different frequency at different sort of layers of the slice itself. And we can integrate this frequency function to tell us something about the phase. And so if we just integrate that frequency from 0 to tau RF over 2, which is from the middle of this slice until the end of this slice, it tells us about the amplitude and time of the gradient pulse that we need to use for rephasing. So this term here contributes this total phase dispersion. So it depends on gamma, the amplitude of the gradient, the duration. And so the gradient amplitude and its duration are something about its area, right? And then it depends on specifically where you are on the slice for how much phase you get through the slice. So we have to design this gradient here has to have an equal and opposite area as that which is contributed by the slice select gradient itself. Is it okay?
Didn't get to see everything. That, so the upper limit of the phase integral is the duration over 2.
Yeah, it's tau RF by 2.
Just making sure, because like that's what you said conceptually. So.
Yep, no, that's right. And so here, the final expression I'm thinking of here is, well, what if the GZ waveform is just a rectangular waveform? So then it's just this area times its width. That's the simplest case. We've already seen it. We've already shown it that, of course, we don't use rectangular gradient waveforms, right? They always look trapezoidal because we can only slew so fast. And the rate at which we slew is actually, somewhat significant compared to the durations of things that we apply. So, okay, so what matters here? Well, all that matters is that the area of that gradient be equal to the area of sort of the first half or the second half of the gradient waveform itself. But you could achieve this area in different ways, right? The maximum gradient amplitude was dictated by the slice that we wanted to excite, right? So we couldn't just simply use our maximum gradient amplitude, which might be somewhere up here. If we used our maximum gradient amplitude, what happens to our slice thickness? It gets thinner, right? So we had to pick this for a specific reason, to excite the slice thickness that we had in mind, right? But what does that mean? Well, it means that this gradient here could actually be shorter, right? All it has to do is have that amount of area. If it has that amount of area, it will undo this through slice phase, and everything's good. And so the strategy for doing that is to tighten it up as much as you can by slewing for longer, and potentially slewing all the way to your gradient maximum strength. You might plateau for a little period, and then you just ramp back down. But the point is that those areas still match, right? So the refocusing area here just has to match half the gradient area that's on top. And so that's one way of allowing you to scan faster. So the slice-like refocusing gradient really should be as short as possible. You just want to kind of get it over with, right? But it's going to be limited by whatever your Gmax is, right? You can only go down so far, and you can only get there so fast, depending on your slew rate. Yeah? Okay. So let's think about the phase encode gradients. So this we saw already. The phase encode gradient, the magnitude of it changes with each TR, and it can be played with other gradients. I'll sort of make that more clear a little bit later. But the phase encoding gradient will contribute this linear spatial variation of the phase. It adds a linear spatial variation of the phase to the signal or to the slice that you're trying to image. And we need to do it after excitation, right? So we have to excite the spins, of course. And of course, we're trying to encode some spatial information in the signal that we receive, so it has to be done before readout. But it's typically associated with Cartesian imaging. And we can do this for 2D imaging, where we just phase encode in one direction, or we can do it for a three-dimensional volume and phase encode in two different directions. And typically, there's only one phase encode step per echo. We can go through this. Okay, so this is the sequence, again, that we have in mind. And we know that the phase encode step is just related to the integral of the frequency that we're applying, right? Everything is, phases are related to frequencies through their integral, and the frequencies in MR are typically related through something like gamma times the gradient amplitude times some position if it's a gradient, or just times the field strength if it's a field. And so this relationship just says that the phase for the phase encoding gradient that you'll get depends ultimately on something like gamma times the gradient amplitude for the phase encoding gradient times the duration of the phase encoding gradient times the position that you're at. Are you really far away from isocenter or not so far away from isocenter? And this was our sort of standard definition for how k-space relates to the time integral of the gradient waveform. And if we just have constant sort of rectangular-like gradient waveforms, then this integral simplifies to just being the amplitude times its duration, right? So we have a nice simple relationship there. And so that's why we can relate it to the ky that we're phase encoding for. So let's go back to something that we've seen several times. So we know that the field of view is 1 over delta ky. And we maybe want to encode that with a total number of phase encode steps, right? We have to decide. We pick our field of view to match the object, and then we pick the number of phase encode steps. What does the number of phase encode steps actually dictate?
Matrix size.
It's our matrix size, and so then that's related to what? Resolution, right? So usually we have a target resolution. We have a target field of view to match the object, and then some target resolution as well. And so delta ky just describes, how far we're moving between phase encode steps, and we can number those steps from the first step that we choose to acquire all the way down to the total number of phase encode steps. And we obviously have to go out to some maximum ky position. The ky max that we obtain is related to what? It's higher and higher spatial frequencies, so higher and higher spatial frequencies mean more and more resolution, right? So we can decide if we want to go all the way out to here and get really high resolution imaging, or if we only need to go out to here to get the spatial resolution that we want for a particular image. So the delta ky, the step size here, this equation here just comes from this expression, because the field of view itself is just the number of phase encode steps times delta y. This is just the matrix size anyway, right? So what's your pixel width or height, if you will, and then how many of them do you have? And so we can see that our delta ky in real units ends up being sort of something like inverse centimeters. We could choose centimeters as a pretty default unit to use. And so you have small fractions per centimeter in terms of the frequency that you have. We can then look at trying to figure out, once we know what our delta ky is, we can figure out what our ky max is. And the ky max is really just related to the number of phase encode steps. Sometimes you subtract one, sometimes you don't. It depends if you're trying to acquire this middle line of k-space, or if in fact you have two lines of k-space that straddle the middle of k-space. There's different. This example here has 5 lines, right, of k-space being acquired. The example mathematically here would be if you only had 4 lines of k-space you were acquiring, so you were straddling the middle of k-space. Anyway, the delta k max that you're going to get to is basically half the number of phase encode lines you have times the delta, right? So how far up you get here is just half of your lines, and then how many steps did you actually take to get out there. And what you'll see just in working through this, if we say 128, say we want to acquire 128 lines, we know what our delta ky was from having calculated from the field of view and the matrix size. You'll end up getting a ky max of something like 5 inverse centimeters, right? So that's like that's something like half a millimeter or half an inverse millimeter, and the spatial resolution that we spent, right? So 0.1 centimeters is 1 millimeter, and so here we're at about twice our Nyquist sampling criteria. So we're should be meeting the Nyquist sampling criteria for sampling in the phase encode dimension. So in general, then we can specify for every ky that we want to acquire, we're indexing through m. That's like m from 1 to 2 to 3 to 4 all the way down to 128 or whatever. Then that's just going to increment by the number of phase encode, the total number of phase encodes divided by 2 minus whatever your index is times the delta ky that you're trying to achieve. Okay, so how do we actually design the phase encode gradient? Well, normally you're going to calculate your ky max. That's going to be dictated by the resolution that we're interested in having. And so the resolution is defined by how many phase encode steps are you going to opt for, and then what's the field of view that you need to encompass the object. And that helps you define, obviously, the largest phase encode step, and consequently the largest gradient. So normally we design the gradient waveform just for that largest step. If you can get all the way out to the edge of k-space, then you can figure out how to kind of just scale, linearly scale that area to get to the other points in k-space. Once you know how far out you have to go, then you can design a gradient, design the shortest gradient to get out that far in k-space. So we have to know the amplitude of the gradient we need, or the gradient area, and we want to do that as quickly as we can in general, right? Just for the purposes of having faster sequences. And then we can just linearly scale whatever gradient area we have for all the other steps. We can use half that area to go half as far out, right? A quarter of the area, etc. And the advantage of that approach is that by scaling the gradient waveform, you're keeping the sequence timing constant from TR to TR. So instead of trying to use the maximum gradient amplitude every time, where you could have slightly different, you could have a really short phase encoding duration for those really low phase encode steps. That would change the TE and TR every single time, and that's generally not good for your local signal behavior. This is just going a little bit back to the book. So we know that delta ky is going over the field of view, and then we know that that's actually related to the delta gradient y step. How much do we have to increment the gradient amplitude to work our way through a delta ky that's specified by the field of view? And so you can actually work out just algebraically, what's the ky max that you're actually going to need to get up to your, say, top or very bottom phase encode step. And usually what we would want to do, if you look at what's happening here, you have the number of phase encode steps times delta ky. So that just tells you how far out of the k-space you have to go. And then this substitution here lets us introduce the idea of the gradient amplitude, or the gradient step amplitude, and the duration of the phase encode step. Ideally, you want to use, when you go out to that maximum ky phase encode step, you want to use the maximum gradient amplitude. And so you just let the total number of steps times the step size be equal to your maximum. You might as well use your maximum possible gradient amplitude, because that'll let you get out, that'll let you phase encode for the shortest duration that you possibly need to. And so from this assumption here of using the maximum gradient amplitude, then you can calculate the duration of the phase encoding gradient. And the only thing that's maybe important here, aside from the algebra, is that you'll see that the phase encoding gradients themselves are also really short. Right? They can be less than a millisecond, depending on your spatial resolution, your gradient performance. And so you see it in this diagram here, but basically what we did was design this gradient here. We figured out what was the maximum gradient that we needed to get up to the edge of k-space, or rather we wanted to use our maximum gradient strength to get up to the edge of k-space, and then we had to calculate the duration for the phase encoding gradient. And then we want to keep that duration constant, right? It's easier, it's better for the sequence overall to keep that duration constant, and so we can just cut the area in half, for example, to go half as far up into k-space, and then get our region across. And then for sequence efficiency, the slice select rephasing gradient and the phase encoding gradients can overlap. There's no reason you can't do these two things at the same time. They don't have to be sequential. If you think about what's happening to the spin system, you're simultaneously sort of taking away that spin that was in the through slice direction, but at the same time using a different gradient on a different axis, you're nominating to also encode the signal with a specific amount of phase that helps you with the phase encoding procedure itself. So there's lots of, sort of see in the slice select design and the phase encode design, a lot of it is regarding optimization of your timing, trying to do these things as quickly as you can for the purposes of scanning as fast as you can. Okay, so then the last gradient in that whole sequence is the readout gradient, right? And so now you'll notice again, there's the readout pre-phasing gradient here, right? We needed this pre-phasing gradient because it helps us move out into k-space. The phase encoding gradient moves us down in the ky direction, and the readout pre-phasing gradient moves us out in the readout direction. And then it's this readout gradient itself that just moves us across k-space. That pre-phasing gradient that's applied there, that also can be done simultaneously, right? And so we get some sequence efficiency by overlapping all of these gradient waveforms rather than playing them sequentially. Things would just obviously lay around a little bit. So how do we go about picking this? Well, we talked about high receiver bandwidth before and the sort of advantages and disadvantages, right? High receiver bandwidth means we need to use stronger gradients, and that gives us a large range of frequencies across the field of view. I can choose a no gradient, in which case I should have no frequency distribution across the field of view, or I can choose a stronger and stronger and stronger gradient and get more frequencies across the field of view, or in fact across the pixel. We sometimes talk about the pixel bandwidth. And we went through this already, but higher bandwidth will give us less chemical shift, but also lower signal to noise. But one advantage, because of the shorter acquisition time, but we might end up with shorter echo times, which could help the signal a little bit because we're moving across k-space so fast. So the change in frequency across the field of view, right? It just depends on the gradient strength that's being applied, and then what is the field of view of the object that you're trying to image. And so this delta frequency here is what we call the receiver bandwidth. And the receiver systems that we use in MR typically operate in the tens or hundreds of kilohertz range. It depends a little bit on the manufacturers and how they specify these things, but it's in that ballpark for sure. And then of course we pick our field of view, right? That's something that we always have as a design criteria. And because there's some direct implications of how you pick your receiver bandwidth, this is always the parameter that's freely available to be chosen on the scanner. Whereas the third variable would be the gradient strength. We're going to pick that and calculate So how do we go about calculating? Well, you can algebraically just rearrange this expression so that you could, for a given receiver bandwidth and a given target field of view, you could estimate the gradient strength needed, for example, during the readout period. Here, I just put gamma in terms of hertz per Gauss. It's a little bit easier sometimes than megahertz per Tesla. And so if we have a receiver system that's sampling the signal at 3200 hertz or 32 kilohertz, and we have a typical field of view of, say, 30 centimeters, big enough to image the head or something like that, then the gradient strength that we would need for the readout plateau is about 3 Gauss per centimeter. So it's reasonably strong, but again, our range of possible gradient amplitudes is obviously from 0 up to 4, 5, or 8, depending on the system that you're actually using. So the other thing that we have to be mindful of is what's the sampling time for every K point that we acquire, and that's just 1 over the receiver bandwidth that we use. So the dwell time at every point that we sample is only about 15 microseconds. So really, it sounds really, really, really short, but of course you need hundreds of these to get out the data that you actually want. And so the time for the readout plateau duration is the number of readout points that you're going to acquire in your matrix, and then what's the delta t for every point that you're actually acquiring. And so if you have 128 points, right, yeah, that looks right. So this will be about 2,000 microseconds, which is only about 2 milliseconds. So it'll take you about 2 milliseconds to do the actual data acquisition part of your experiment. There's all this other stuff for exciting the spins and encoding the spins, but the actual data acquisition part of it is only about 2 milliseconds. And so if you get into sort of sequence design and sequence optimization, you're frequently trying to acquire data for as long as you can to whatever criteria you have, and spend as little time doing all the other stuff as you can. Because this is the only time you're getting information that's really useful for forming the image, right? So if we look at the complete readout gradient that we need to put together, we know how to define the plateau of the readout gradient. It's dependent on the number of samples and the dwell time for measuring each sample. And then some other limits come into play, right? It's still a question of how quickly you can ramp up to your maximum gradient amplitude and how long it takes you to ramp down. So that would help you design the overall gradient plateau during the readout period. But we also know we have to do the readout pre-phaser. And so the readout pre-phaser, again, the area here just has to match half the area of this gradient plateau here. And you would typically want to design this to be as short as possible by using something close to your maximum gradient strength. But you still can't exceed your slew rate, so there's some constraints on what that can end up possibly looking like. And so it says it at the top here, but if A prime, if the area of this gradient here is equal to A, that's going to give you symmetric K-space coverage, right? You will have moved out a certain distance in K-space and then moved back by the time you're forming your echo in the middle. If you allow A to be smaller, then you're actually going to have some asymmetric readout gradient. And then again, we saw it earlier, but this gradient waveform here can overlap, right, with the phase encoding gradients or the slice select rephasing gradient for the purposes of being time efficient. Okay, so that's, we're moving through that pretty quickly. Questions about sort of how we calculate the different parameters for designing the slice select, the phase encoding, the frequency encoding gradients?
Could you move to the previous slide? Where is the delta F in frequency difference for? Here's which is this? What is this delta F?
This delta F is like the receiver bandwidth.
Receiver bandwidth, but why there's a 2 times the 1 over 2?
There's different ways of specifying the receiver bandwidth, right? And so a lot of the scanner platforms, they'd actually refer to this as the receiver bandwidth as being plus minus 32 kilohertz. And so the total frequency range of plus minus 32 kilohertz is actually twice 32 kilohertz. Sorry, I didn't get into that. But again, this is the frequency at which you're doing the sampling of the signal during the readout, and you can choose that, right? You don't always have complete freedom over choices, but there'll be some discrete bandwidths that you can choose from on the scanner, so to speak. But it means, all these systems are acquiring data over very, very short periods of time for each point that you're, each dwell point. And I guess I should point out that there's a limit here, right? Meaning that, that must have been here. Let's see. That's okay. Okay. Question?
Do you calculate the ramping time for the A time? Like next time, yeah.
Yeah, so again, what matters is just the areas, right? Because the areas are what contribute when you integrate the frequencies, right? It's the area of the gradient waveform that contributes to the phase.
Yeah, but when you calculate, you didn't calculate the ramping time for the TRO, right? Like you do that for A time.
Yeah, so I didn't go through the steps here. It would look a lot like, say, the slice select gradient. Tell me if this answers your question, right? So the first thing is you would, if you're just designing this gradient plateau first, right? Then this is typically going to be slew rate limited. You're going to ramp as fast as you can until you get to the magnitude that you need.
So you mean you don't care about the ramping time there because it's too short? You're going to
Well, okay, so I care about, no, you care about the area. Why? Let's see. Oh, that's a great question. I see what you're saying.
Yeah, because for that one, I think you calculate.
Yeah. No, right. And so for the readout gradient itself, yeah, you do care about the area, right? So
Yeah.
this area here contributes to you moving through K-space,
Yeah.
right? It's different than the slice select gradient.
But for the slice select gradient in the last ramp time, you also contribute to the dephasing.
Yes, because the spins are excited at that,
Yeah.
and so they're still dephased by that ramp down on the slice.
Yeah, so I'm just quite curious. This A doesn't equal to that A, something, or you don't care about that.
You mean
You
are I'm not sure if I understand what you're saying. These areas are unrelated to slice select.
Yeah, but in slice select, you didn't care about the ramp time because when you draw the area, you also draw the area like under there. Okay, so
It's okay. I mean, let me just try to be clear. So the lines that are here are only to indicate what's the time for the readout duration, right?
okay.
And maybe it's confusing, but the area is supposed to refer to this rectangular area and the triangular area.
Yeah, but for the slice selection,
Yep.
the area because your outpost just start there, right? So which means
Yeah.
for the front ramp area you didn't care about.
Yeah, that's right.
Yeah,
So
that's
this
the
area
way-
doesn't contribute anything to the spins.
Yeah.
You just have to ramp up, of course, to get to that
But
amplitude.
for the later one,
Yeah.
it's contribute to the dephasing.
Yeah, because at this point my spins are excited already.
So when you calculate the A, do
Yeah.
you count that one?
Yes. Yeah. And so this is, say, that's the middle of my gradient
Okay,
amplitude. It should line up with this, right?
Yeah.
Then the area I need is everything,
Cool.
right? Because it's that total area that contributes to possible dephasing. And importantly, it's the integral of that residual gradient waveform, right? Okay. That's a good question. Yeah. So I think we're gonna likely finish. That would be okay. So the last thing to talk about here is actually eddy current. So this is a topic. It'll be important when we come back for the phase contrast lecture, which is, I think it's next week. Maybe it's 2 weeks. But I'll say we'll get into this a little bit. So the gradient hardware itself, we've seen this tear down sort of several times in different ways. Anytime you excite, anytime you run current through a conducting structure like one of the gradients, you obviously can generate magnetic fields, right? And we saw an example of this even in the lab, right? We had this aluminum plate, and the aluminum plate was falling through the magnetic field, and that was generating currents. The field's fluxing through the conducting structure, and that creates a current, and that current creates a field that in fact opposes the B0 field, so it fell very, very slowly. Anytime we fire up one of the gradients in particular, right, the X, Y, or Z gradient, they're producing fields. Those fields are going to permeate other conducting structures in the scanner. It's very difficult to control that, although the hardware and engineering design tries to minimize it as much as possible. So anytime I turn on a field, anytime I have a flux, I can create a current in some other structure. That other structure will have a current and consequently generate a field, and we usually call those eddy currents or eddy current fields, right? And so what I want to, that's sort of partly describing the origin of it, and then we'll get into sort of what kinds of problems that actually has. And so that's got exciting. Okay, so the gradient coils induce currents in nearby structures while they're slewing, right? That's when you have the time rate of change in the magnetic field, so you can actually generate a field effect. And so this might be my gradient coil, and we typically think of the gradient coils as being resistive, inductive structures. They don't typically have much capacitance, although they probably have some very, very low capacitance just by their design. So the simplest sort of understanding of this is that you run a current through your gradient coil. Of course, it has some resistance, and now you know it has some inductance. That'll generate a magnetic field that we use for all kinds of things, spatial encoding, right? But those fields themselves will, of course, impart fluxes into nearby conducting elements. What conducting elements am I talking about? Well, it could be like the cryostat that contains all the liquid helium, right? It can be other shim coils that maybe aren't actively turned on, but they're still conducting structures. It could be the coil that you're using to image the patient. It could be all kinds of things, right? There's, for better or for worse, a lot of conducting structures, right? So these could be any number of different conducting structures. And if I create a field in these, then I can induce a current. And that current, because this is an inductive resistive structure, that current will be sort of built up to sort of some maximum during the time that I'm fluxing, and then that current would decay. It's an LR circuit, so that current will decay like an exponential once the gradient here is maybe turned off, right? So that's the kind of underlying principle of what's happening. Sorry for the background garbage there. Okay, so let's think about the ideal gradient waveform, right? What do I mean by ideal? Well, we saw lots of trapezoidal gradients in putting together the slice select and readout gradients, for example. So that's typically what it's programmed to look like, right? You punch in your code, and that's the gradient waveform that you would like to generate. The eddy currents are only generated while you're slewing. So this is what I would call the slew rate waveform. You have a maximum slew rate that accords with the slope of this gradient waveform for that period of time. So you have some maximum slew rate that's, in this sense, positive, and then at the end, and then while you're plateauing during this gradient, there's no effective slew, right? The gradient's not changing as a function of time. And then at the very end, you turn the gradient off, and so that gives you a negative slew. These slew waveforms, these will induce, during these periods of time, currents in those nearby adjacent structures. And they, in the positive sense, say of a positive slew rate, you might generate a negative current, an opposing current. And that current will build up as long as you're slewing because it's a resistive inductive circuit, or it's modeled as one. But as soon as the slew rate is off, as soon as you're done slewing, then the current that's in that LR circuit will just decay according to some time constant. You don't know the time constant. It's related to the resistivity and the inductance of the conducting structure, but it has some resistance and inductance. That same structure, when you ramp down this gradient here, you'll also induce another current in that conducting structure, but because it's in the opposite sense, the current maybe ramps up this way with the same time constant dictated by the L over R, and then it will decay as a function of time. And so these are the eddy current gradients. You can think of these as being additional gradient fields or additional B fields that appear in your system anytime you're slewing. Right? Anytime I slew, I induce a residual or an extraneous field, and that field builds up over a short period of time, and then it decays over some other period of time depending on the time constant. And so unfortunately what you end up with is this is your desired waveform, but because of these eddy currents that are generated in other nearby structures, what you get is the superposition of both of those. All that matters is the field at some specific position, right? This gradient should be generating fields in a very specific and linear way, but because of the eddy currents, you'll end up getting gradients that actually have some unusual timing behavior. And it's simply just the addition of your ideal gradient waveform with these gradients or fields that are coming from this, this inductive coupling between those underlying structures. And so anytime we don't have, anytime our actual gradient waveform deviates from our ideal gradient waveform, we're going to have some kind of artifact, right? In principle, what it means is, maybe this gradient waveform, this kind of gradient waveform would move us very linearly through K-space, so we're getting a line through K-space, and we know exactly how to interpret that data because it follows as points in our K matrix. But as soon as our actual gradient waveform deviates from that, it means we're crossing through some like arc in K-space, right? We're not getting the data that we really want, and so maybe this is my intended data. I'm supposed to acquire this KY line, right? What I actually ended up acquiring because my gradients were imperfect is maybe I got a KY line that did something like this. Right? That's where this is my actual trajectory. And so this is ideal. This is actual. And it wouldn't be so bad if I knew I went through that course in K-space, but I don't know that, right? What I told the scanner to do was this ideal gradient waveform. And so now I've acquired data that went through some other trajectory in K-space, but I didn't know any better. And so I took this data and I put it into this location in K-space, because that's all I knew what to do. This is the trajectory I intended to acquire, so I must have gotten it, right? But in fact, the imperfections in the system will have you drifting somehow through K-space. And so anytime you don't identically put the acquired K point into its exact location in K-space, you're going to get some kind of artifact. And the question is, what does that actually look like? Does that make sense?
The question is that the phase encoding has already been done before the readout.
But this is true for any gradient, right? This could be the slice select gradient, rephasing gradient, phase encode gradient, any of them. So what really matters is the contribution. What kinds of eddy currents are generated from all of the gradients before you're forming your echo, because they'll contribute to sort of inaccuracies in your trajectory through K-space. Does that make sense?
The actual gradient waveform is in frequency encoding, right?
It could be.
You don't have the waving thing because your waving thing is changing in your phase encoding. You already finished that part.
So do you mean that during the readout, this eddy current will also affect the KY?
Well, okay. So just think of it this way. This is any gradient.
Yes,
so let's
any
pick one to
gradient.
talk about. Which one do you want to talk about?
But
No, hang on. There's because I got 4 hands up, right?
Say phasing.
So you want to talk about phase encode or frequency encode?
Phasing first.
Okay. So phase encode. So in the phase encode space, this is Kx, and this is Ky. And let's say I have eddy currents that only affect. So my sequence looks like. So you guys are, well, what we're imagining is that for some reason it's only this gradient that generates an eddy current. Okay? Let's not worry about gradients that come afterwards, right? And yet I still have to do some kind of readout, right? So I have a readout pre-phaser, and then this is my readout gradient. If there's something imperfect, if eddy currents cause one of these in particular, right? So let's just talk about the top phase encoding line here, right? If my gradient area is different than what I expect because of eddy currents, right? Then this might be the target line of K-space that I want to get. But now what's going to happen? If my phase encode area is not what I want it to be, I'm going to get a different line, right? So I could be here, but it's still a line, or I could be here, and it's still a line. Okay. Now other things are possible, right? So I just meant this as a very general sort of possibility, right? So how could something like that even happen? Well,
Just can't imagine how.
I had to think about that one. What's harder to show is what happens if you have eddy currents during the readout, right? So then it has to do with how the rate that you're moving through K-space, but along the line.
So maybe it will induce another like a magnetic field in your face.
In the Y direction.
That's,
Yeah.
that's possible.
And then it would be
Yeah,
away.
no, and that's actually a really good point, right? So the Gx, let's say that this is Gz, Gy, and Gx. The x gradient could induce a field along the y direction, right? It depends on what structure it imparts a current and induces a current in. And then the conducting structures of the thing that the current's inducted in, they may look a little bit more like a y gradient than an x gradient. Who knows? It's the cryostat, right? So in principle, any gradient could actually produce a field along any direction. And so you're right, that could give you shifts. What's the point? Well, the point is that you have ideal gradient waveforms that are programmed, and then you have real trajectories through K-space. And eddy currents are one of the reasons you might not get your ideal trajectory through K-space. And so we can look at some extreme examples. Well, this is a little bit more mathematically what's happening, right? So the voltage that's induced in some conducting structure, just according to Faraday's law, depends on the time rate of change of the gradient field itself. And it's an opposing field because it runs this law. And these I think we mostly work through. So you could have some current that you measure as some function of time, and this is a decaying current. It depends on some maximum possible current that decays depending on the resistance and the inductance of that current. So that's why these curves here are shown as decaying exponentials at the end of the slew, if you will. So if it's a source-free RC circuit, meaning you've induced a current in it, but that source of current goes away, there's no more slewing, then this will be a decaying exponential in each of those. For each of the eddy currents themselves is described as some decaying exponential. And any current itself is going to be proportional to some field. Now, we don't generally know that proportionality. In fact, we don't even know the magnitude of the currents that are generated very easily. We just know that this is possible. Actually, measuring these things turns out to be quite tricky, but there are different ways of doing that.
Sorry.
Yep.
So what you say is you generate a field, right? A magnetic field. But on your diagram is a gradient.
Oh, this should be a dB dt, right? Is that what you're thinking?
No, the effect is that you change the gradient shape. You change the gradient waveform.
It's not. So you turn on one of your gradients, right? So let's go back to. When you turn on the gradient that you want, right? It's going to induce a current in some structure during the time when the gradient is slewing, right? After you're done slewing, there's still some current in that structure that's decaying, right? That current will create a field in that structure, and that field is just a field. And so that field superposes with B0, superposes with the gradient field, for example. And you have a target gradient that's turned on, right? So readout gradient, phase equal gradient, whatever. But you won't get exactly that performance that you wanted because of the superposition of this eddy current field with the desired gradient. Does that help? Or is that not your question?
Because this axis is the gradient over time, right? So
Correct.
what you get is a field. Additional field.
Yep.
Equivalent.
Just a field at some position, right? You can have it. You can think of it as a gradient, or you can think of it as a field. The only difference being whether you're dotting with position or not, right? It will in fact have not just an effect on the frequency, but the phase, and then you have to think about integrating the eddy current field to describe the phase effect. But you can think of it as a current, a field, a frequency, or a phase. Unfortunately. Okay. Go through this. I think it's just showing some examples there. So anytime you don't move through K-space in the sort of preferred path or your targeted path, you have different possibilities. EPI is really susceptible to ghosting artifacts, right? EPI was this trajectory. You're moving through k-space as quickly as you can, right? Because of that sort of zigzag trajectory, you're getting your odd lines in one direction, but you're zipping back to get your even lines in the other direction, right? What happens if I take away half my lines in k-space? Aliasing, right? And so if there's any slight difference between the phase encode lines acquired this way and those acquired this way, you'll get these sort of ghosting artifacts that look a little bit like aliasing. Imagine that instead of having perfectly integer separated ky lines, they're just a little bit off from each other. All of a sudden you'll have a ghosting artifact. And eddy currents can give you that small perturbation, right, in your phase encode lines such that you'll see a ghosting artifact. If you turn on really big gradients, we haven't talked about diffusion weighted imaging yet, but if you turn on really big gradients, which you need to do for so-called diffusion weighted imaging, those really big gradients have high slew rates for long durations, and those will create the biggest eddy current fields that you can basically generate. And that can lead to imagine playing really large gradients before your readout. Again, it's going to cause some distortion of your trajectory through k-space, and that may actually lead to some geometric distortions. And then this will get talked about, I think, in one of the phase contrast lecture, that these eddy currents don't just affect the frequency of the signal, but they affect the phase as well. And so you can get some phase effects, which are important if you are trying to use the phase information in the MR signal to measure or quantify something. Possible to use the phase information to quantify the velocity of moving and flowing spins. And so an example of this is like this, and this is a very real sort of distortion artifact for so-called diffusion weighted imaging. So the image on the left is a T2 weighted image, right? CSF is pretty bright. CSF has a long T2. Long T2s are bright on a T2 weighted image. And what's being shown on the right-hand side are some kind of noisy EPI images, and they're diffusion weighted. In diffusion imaging, you actually apply the gradients, very strong gradients in many directions. So every image is showing the application of a different diffusion encoding gradient. Maybe the diffusion encoding gradient is along X or Y or Z or some linear combination. And the point is that with every direction that you use for diffusion encoding, you get a different distortion in the underlying image. And the distortions are pretty big, right? You shouldn't see any of this head wiggling around at all, right? That's obviously unexpected. Posteriorly, and that's purely because of these large diffusion gradients that cause deviations on your trajectory through k-space and can actually result in pretty large image artifacts. So different ways to sort of deal with eddy currents. There's hardware approaches, right? So you can do so-called shielding of the gradient coil. So you try to minimize the interaction of one gradient coil with any other conducting structure, so-called shielded gradient. You can also do what's called waveform preemphasis. And so we know that those gradient waveforms are distorted. And if we know enough, if we can characterize the system carefully and well enough, then we can actually put a distorted waveform in so that the distortion that we put in plus the distortion that the system adds actually gets us back on track to the more linear trajectory that we want. So we call this waveform preemphasis. You're modulating your gradient waveform so that your outcome is what you want. Treating this, you sort of know something about the black box that the scanner acts as. So there are hardware approaches, and those are pretty well dialed in. There's also so-called full sequence approaches, right? You can change the sequence that you're using itself. You might be able to improve things by derating the slew rates, so the amount of current that's generated is proportional to the slew rate, so you can probably push those fields down in part by lower slew rates, but that may or may not be acceptable for your strategy. We won't get into the details of this, but there are some other tricks for sort of minimizing eddy currents by trying to get them to offset. If you generate one eddy current, can you generate an equal and opposite eddy current such that they cancel each other during the readout, for example. And then secondly, you could do something in reconstruction, right? You'll see this in the phase contrast lecture that you could sort of measure something out the eddy currents and kind of deal with them, subtract them such that they don't corrupt the overall image information. Or you might in fact be able to sort of predict them in some ways based on treating the overall system as linear time invariant or somehow characterizing it as the transfer function of the system itself and then subtracting those effects. Okay, so that wraps up gradients for today. You're in the middle of handing in your lab assignments, and then we've got a new homework assignment that's posted and a new lab on Tuesday. So things are a little busy for the next bit. I'll take it from there. I'm around for a bit if you have questions. Otherwise. So you have to do some kind of system optimization. So you have to develop strategies. Eric's strategy is really good.
一定要这样，
This is the case-based trajectory.
没有吧？因为一定要必须要真实的
Figure out this transfer function.
哦，这个是对对对对，这个是反方面。
这个人是要这样的，然后就这个，
But it's not very satisfactory.
所以好像是做这个，他就认为啊，对，任务的就是2倍，所以根本就没有证明。